just a little bit of about myself. I've actually obtained my PhD from the National University of Singapore, so I think I spent quite a good deal of my life looking at security stuff. And I've also written papers on how TEs can be broken. So I kind of like thought that, hey, since I've written papers that on how TEs can be broken, maybe I have something to share with the kind of like community in the Web3 ecosystem. Like maybe I can share on how TEs are actually useful, even if they can be broken. So here I am today. And by the way, cats are awesome. And I heard that there's like a lot of cats in Istanbul. I'm looking forward to like play with them. So anyway, with that out of the way, right? A kind of like rough structure of today's talk is we'll first take a look at like what exactly is a TE, like what makes up a TE, what are some of the properties that we would like to see from a TE. Then we would actually move on to see how are some of the TEs being implemented, what are some of the underlying technologies that actually enable us to build such interesting primitive that we can utilize. And then finally, I will kind of like end off the whole presentation by talking a little bit on why TEs are important and like what are some of the pitfalls or some of the ways on how we can make use of TEs in our development, in our product ideation, or even pushing the frontier on how we can utilize TE to improve the security of the entire Web3 ecosystem. So, what are trusted execution environments actually? So, imagine we have this fantasy world. We live in reality, right? It's boring cities, skyscrapers, or like concrete buildings. And imagine that in the middle of this city, there is this magical enclave. There's a portal that allows someone to kind of like transition between this magical world and our mundane world. And this magical world is actually isolated, separated from the normal world. Whatever that happens in this mundane world, you can think of it something like, I don't know, Harry Potter or like Stranger Things, you know, the mirror world in all these shows. Basically, things that happen in the magical world, the muggles or the normal people living in our normal mundane world would have no idea at all. They are actually oblivious to what is happening within this magical world. And because of the magical nature of this world, the rules and laws of the land is actually enforced. That means anyone that chooses to enter the portal and go into this magical enclave would have to follow certain rules, and it is enforced by the nature itself. So you can imagine that this magical enclave is a trusted execution environment. So I think in the morning we actually have another talk on like trusted hardware. We have seen some examples like Nitro Enclaves, Intel SGX. There are other kind of like TE solutions or trusted hardware solutions like ARM Trustzone and AMD SCV. But are these trusted execution environments? Well, the answer is not really. They are instantiations of trusted execution environments, but they are, I mean, you can think of it as they are a subset of what we call trusted execution environments. So if you kind of like look at CT or, I don't know, CX now, CryptoX, people tend to directly associate Intel SGX with TEs, but TEs in general are a lot more than just Intel SGX. So, like what I've mentioned before in that analogy of that magical enclave, any technology that actually allows us to create this isolated processing environment that enforces the integrity of the data or code and preserving the confidentiality of this data and code, we can say that this is a TE technology. This actually means that TE as a technology is vendor agnostic. So in the example that I've given before, we have Intel, we have AMD, we have Amazon, there's ARM, there's even like RISC-V TEs, like Keystone is an open source kind of like TE framework. So we are not really like locked into a specific vendor if we choose to utilize TE technology, because we would require the TE to provide us certain guarantees, but we are free to choose among all the different vendors. There are open source projects that are kind of like working very hard to ensure that there's a layer of abstraction above all this actual hardware implementation of TEs, such that it makes it easier for us to develop. But again, this is really vendor agnostic and implementation agnostic. And finally, TEs, because of the diverse nature of its implementation and vendors, each of them actually have really different security threat models and guarantees. So again, like in the morning, I guess the speaker did a really good job on explaining the threat model of Intel SGX, where the operating system is considered malicious. But in another, what's that called, TE implementation, like AMD SCV or ARM's CCV, the operating system is actually considered as part of the trusted compute base, or rather, it's part of what we deem as trusted software, and it's actually running within the secure enclave itself. So I guess as a developer, as a project, when we choose to utilize a TE, one of the things that we have to consider is really like, what are some of the guarantees that we want to give? What are some of the assumptions that we want to make? And from there, we actually choose the appropriate TE technologies to kind of like back our solution. So with that out of the way, right, you must be thinking, like, how in the world can we actually achieve this? So before going into the magic behind TEs, I'll kind of like explain a little using a small little example on why TEs are actually important, or it's useful in terms of how we can use it to secure our products or our protocols. So let's say I have the most common architecture now is the von Neumann architecture. So your code and your actual data are actually all just data that resides in memory. So you have a CPU that will actually fetch the code as instructions from the memory, execute it, and it might actually read and write into variables or data that's stored in that same memory. So let's say I have a piece of memory, that there are certain instructions that is written to it, there are certain states that are written to it. For example, A would send B 10 tokens, A would send C 20 tokens. This is like my program. And then there's a state for A, there's a state for B. The CPU would read the first instruction and execute it. Notice here that anyone that has access to this memory, for example, like the operating system or the operator of this service, is able to actually pick into the memory and see that, hey, A actually has 100 tokens in its balance. And this same operator or operating system or like the owner of the server can actually override part of the instructions to say, like, you know, instead of A send to B, I'm going to say that A would send to E and 100 tokens. And there's no way for the CPU to actually identify or realize that this change happened. And the CPU would like gladly just read off the instruction from the memory and say that, hey, I see A to E, 100 tokens, I'm going to execute it. This is the reason why in the kind of like non-TE sense, the integrity of the computation cannot be guaranteed. So how can TE actually help us in this? Well, imagine the CPU actually contains this one secret ring. And this secret ring has certain powers in it. And the CPU is able to use the power of this ring to create a kind of like a bubble where any data that is within this bubble is actually being encrypted or being like abstracted away. And at this point in time, when Eve actually tries to read the memory, she won't be able to understand what is actually written in there, like What is that? I totally have no idea. This provides the confidentiality nature of TEEs. Similarly, if Eve tries to do what she did previously, like overriding part of the program code, the CPU would actually be able to identify this because the instruction is actually encrypted and encoded in a particular manner that only me with the secret ring would be able to decode. And at this point in time, the CPU can actually raise an error to say that, hey, there's something wrong with the program that I'm executing, and I'm not going to continue any further until I'm able to verify that this is indeed the proper code that I can execute. And you know what's the best thing about this? That secret ring that the CPU has, or that the hardware has. So, for example, someone might actually want to ask, hey, which one of you is the real CPU? Because, you know, there are imposters all over. This is a decentralized network. Anyone can participate in this, and how can we actually identify who is the real person, or who is the real CPU? Well, Eve don't have the secret ring, and she can claim that she is the CPU, but she has nothing to back her claim with. However, the CPU with the secret ring is able to say that I am the CPU, and I have this ring. I can create a proof of the ring, or I can sign certain cryptographic material with that ring to prove to you that I am indeed the real CPU. So, I'll kind of like skip this. The kind of like fundamental nature of what TEEs are is math and cryptography. There's nothing magical about it. You have basically a secret key that's embedded in the hardware, or a physical unclonable function that is embedded in the hardware itself, in the silicon. And you use that to generate a secret. You can use the secret to kind of like encrypt the memory to provide confidentiality, to create like message hashes to ensure that your data is not being manipulated or changed. So, with that, we kind of like ask the question, okay, great, now I have this TEE. How is it useful? Like I mentioned, that secret ring is actually this root of trust that is embedded in all our hardwares. So, just have a show of hands. Which one of you actually have ever used a TEE in your day-to-day life? Oh, we have. Any one of you have an Apple iPhone? Just raise your hands, don't be shy. An Android phone? Okay, so if you have any of those devices, you have used the TEE. The TEEs are actually really commonplace in our life. Your hardware ledger wallets are considered TEEs. Your secure enclave within your Apple iPhones. Android have the ARM Trust Zone, or like different phone manufacturers will have different branding for their TEEs, but they are part of our everyday life. And this actually allows us to perform a lot of things. I think one of the kind of like contention for TEEs is that, hey, we have zero knowledge proof, right? We have succinct proofs. Why can't we use it to ensure like the integrity of the computation? Yes, we can do it, but one thing that TEEs can do that ZKPs can't is actually an extension of the user's trust domain. So if we are actually using a kind of like a succinct proof system, the trust boundary of the user is actually the user's machine itself. So when I kind of like supply the private inputs, I have to do it on my own machine. I can't just do it on some rented machine because I don't trust the machine. With a TEE, this trust can actually be extended to any machine with a trusted execution environment. Of course, that trust might actually be discounted. And basically, TEEs also provide for a performant confidential compute compared to succinct proofs because it's a lot more performant. So I'll just kind of like do a very quick run through of things to be aware when dealing with TEEs. Because of the kind of like different nature of TEEs, that there are things that us as developers or product owners have to be aware of. For example, TEs, because of the trust domain separation between trusted and untrusted, introduced the idea of Iago type attacks, which is like when you get a value from an untrusted domain, that value itself can't be trusted. So you have to do additional verification on it. There are TCP-related consideration and side channel attacks, like what we have mentioned. A lot of the kind of like fear of TEs is actually on these side channel attacks. And of course, there's also the fault injection attacks. With all of that said, how can we actually use TEs effectively? Now, one of the things that we can do is to consider the environment which the TE is operating under. And for example, if we are worried about fault injection attack, we can mandate that TEs be only used in a cloud setting. This way, the operator actually don't have physical access to the TE. We can also consider security threshold schemes and make use of TEs to implement that. But in general, what I would want to raise as an awareness here is really to make use of the strength of TE, which is to enforce integrity. All the attacks that I've mentioned before, for example, your side channel attacks, would reveal data. But if what we want to do is just to make sure that my computation is correct, then I think TEs are a really good fit for it. For example, as a co-prover for ZK rollups. So I think my presentation is at the end, and my kind of like final message to all of us here is to really embrace TEE and let it be a useful tool in our toolkit to enable a more secure and usable Web3. So with that, I thank you all for your attention, and I'll be around for the entire TrustX event. Feel free to just come up to me and we can have a conversation on how we can use TEs to improve the product or some new ideas. Thank you very much.